third session on Graph Database. I'm thrilled to introduce our next speaker for today, Will Evans from Graphable. Will Evans is the co-founder and CTO at Graphable. He has 10+ years of experience with the Java platform, holds both BS and BA degrees in computer engineering and English, and has helped hundreds of companies derive value from technical solutions. With his years of consulting experience, Will excels at distilling complex problems in any industry to their base and working to create elegant user experience-driven solutions, regardless of the technology. Welcome, Will.
Hey, thank you very much. I assume that everyone can hear me. So thank everyone for being here and for CTech for organizing this. It's a great collection of presentations. As mentioned, I'm Will Evans, co-founder and CTO of Graphable. And today I'm going to talk about deploying highly connected data at scale for novel insight. As we get started, I just want to briefly cover the plan for today's session. It's a lot, so I'll try and move quickly. I don't know if we'll get us ahead of schedule, but I'll try and at least not go over. Just so we're all on the same page, I'll walk through a brief overview of Graphable so you know who we are and what our experience is, and then I'll talk about graph databases and Hume with some general guidelines for thinking about your use cases. And finally, I'll cover some specific use cases we've deployed with customers in the federal, DoD, and government adjacent spaces. My goal for today is that you take away an understanding of the power that graphs and custom solutions provide in extracting value from large, highly connected data sets, and that you have some specific use cases in your mind to evaluate your needs against. We founded Graphable 5 years ago to solve an issue we saw in the industry around delivering excellent consulting solutions for extracting value from data. We've focused through the years on the business intelligence and graph spaces, including the intersection of the two, which is a relatively new phenomenon. And we work across an extremely broad variety of clients, all centered, however, around their belief in the value of their data and the need to leverage it. So we've worked with cutting edge startups to DoD, Fortune 5, and throughout all of our projects, we think what distinguishes us can be summarized by our 3 uniques, which is that every project is a partnership. Our team understands and tenaciously pursues the why of a project, and we deliver high value, high touch, excellent delivery. Now that you know a bit more about what drives our experience and direction at Graphable, I want to focus on a brief introduction to graph databases. In a traditional or relational database, information is stored in tables with connections leveraging foreign and primary keys or even join tables between information. In this instance, or example, we have a table of people, we've got a table of locations, and we have a table of objects. From this data, we're able to quickly aggregate and filter our information, but traversing these connections between tables is challenging. Enter label property graph. In this example, you can see that the rows of our tables have been deconstructed into nodes and edges, or nodes and relationships in a graph native store. So we have our blue people, our sort of teal locations, and our green objects, all connected together. In this store, the connections are what we like to call a native first-party consideration within the graph, and our ability to traverse across data grows by orders of magnitude. For one example, we've seen financial institutions traversing networks of individuals to investigate suspicious transactions, and in their cutting-edge relational system, they were only able to traverse a depth of 5 connections from entity to entity. Once they moved to a graph, they were able to traverse to a depth of 45 transactions with faster results than in their relational system. For a collection of reasons, Neo4j is our preferred graph database on the market due to its underlying graph native technology. And while we don't have time in this presentation to dive into further technical details, I'd be more than happy to spend more time on a follow-up comparing it to some of the other offerings on the market. In our labeled property graph, or LPG, data is stored in essentially 3 ways. We have nodes, which are my dots here of object, person, and location, edges, the relationships between them, and key value pair properties that can exist on both nodes and edges. So on a person instance of a person node, I might have a name of Will Evans and an email, will@graphable.ai, and I have the same instance on my relationships. So we store a very rich set of metadata within the connections of our data. Looking briefly at market trends for graph, Gartner predicts explosive growth in the use of graphs in the data analytics innovations, as this technology is currently hitting an inflection point in growth in the market. And so we expect to see 80% use by 2025 over the next 3 to 4 years. After that Quick introduction to graph databases. What is Hume? Hume is built on top of Neo4j and works as a mission-critical graph analytics solution that puts the power of Neo4j native graph performance in the hands of intelligence analysts. Hume provides a simple-to-use interface that allows intelligence analysts to search, visualize, and analyze intelligence graphs. I want to spend more time on use cases today, so I won't go into a full demo of the Hume platform, but this is definitely something we cover on a follow-up as well. All of the screenshots you'll see in our specific use cases are from the Hume platform. Now that we've covered some basics about the power of graphs in Hume to unlock value from your highly connected data sets, I want to share some general guidelines that we've come across in working with our clients so you can glean some of our expertise as you start your use cases. The first thing we found consistently is the need to consider your data scale and composition. Graph databases like Neo4j are for highly connected data. Intelligence and knowledge graph use cases almost always contain significant proportions of raw data volume. And we've seen time and time again, customers bring us in to improve the performance of a massive graph that they have deployed. One of the first things we want to do is actually remove data from it because they're storing document type information in the labeled property graph properties. So if we go back to that key value pair, they might be storing an extremely long string or long list of information in one of those key value pairs, even though that's not being used in the traversal. In large scale deployments, you almost always want to use a multimodal store, even though it's a little bit more work up front, as memory is always faster than disk, and the more of your connections you can keep in a cache will enhance your query performance to get through those traversals, while you can enrich with document data at the end. So favor the labeled property graph for your connected data and use the appropriate store for everything else. One specific example of this that we've seen is in NLP use cases, where we may be doing corporate knowledge graph or processing messages across social media. And we've seen use cases where people up front are storing the raw text in their graph just for ease of use. But over time, and doing NLP on that text at the same time, extracting the relevant entities from it. We're doing things like sentiment analysis, as Quinn was discussing, and they're still storing that raw text in the graph. And what we often recommend in that use case is store your key entities and sentiment as properties or nodes within your graph, but keep that raw text offline as something that can be enriched later in an application. And that allows more of your speed performant memory to be used for the traversals. Secondly, we really want to make sure to consider your use case and your users. There's unfortunately no golden rule I can share for designing graph schemas, but this is a set of questions that we ask in each engagement to identify the best starting schema for a solution, while keeping in mind that unlike a traditional database, your schema is not written in stone. The best schema is your current one, as both Neo4j and Hume are flexible and can be iterated. So you want to make sure that you're considering who are your users, what analysis do analysts want to conduct, what data is needed to meet those requirements, and what queries are going to be written to meet the use case. Oftentimes, the fastest approach we found is to take sort of a V0 approach and to build a schema and ingest some representative data in to test it, and then iterate from there. Rather than trying to nail everything down perfectly before we start getting to the analysis phase, we want to get to that analysis phase as fast as we can, and then iterate again for our full-scale deployment. We've gone over now some of the advantages of graph databases in the Hume platform, as well as some general guidelines in generic use cases. But I want to cover some specific examples for you to think about in your own use cases. The first is a confidential project we're currently working on in the government space around competitive research analysis. The image to the right is an obfuscated version of our schema for this investigation from the Hume platform. And you can see the highly connected nature of the data. So all of these colored entities are obviously our nodes, and we have our relationships labeled between them. We're ingesting in this use case articles, keywords, authors, affiliated institutions, and much more to understand how research is developing within certain organizations or geographies and tracking that progress over time. With all of this data, we've collected a highly connected network of scientific research across billions of entities, and we're leveraging complex machine learning and data science workflows on top to extract novel insight. So we do things like do unsupervised machine learning on top of this graph in order to identify groups of keywords and see how those keywords progress over time. And this is currently in use in applications within the government. And it's a constantly updating project involving time series analysis within graph, and is really on the cutting edge of what we're doing for that sort of competitive research analysis. A second use case that we've deployed outside of the US actually is a tactical crime intelligence solution. In intelligence use cases, we find there are sort of four common schemas as we go back to that generic advice about designing your schema. We find that there are exploratory, domain, tactical, and sandbox investigation types. And briefly, exploratory graphs are built for visualization and exploration of the data across many sources and domains to summarize your intelligence. While domain-specific graphs use schemas that better represent the complexity of a specific domain, like telecom or beneficial ownership, and tactical graphs are operation or investigation-specific graphs where relevant data from both internal and external sources is used to serve a specific activity, often investigated by a small subset of users. And lastly, the sandbox graph is a place where ad hoc data sets can be uploaded and analyzed without being shared. And this is typically before being finalized into an updated schema. In this use case, our customer leveraged a tactical schema for a specific case involving a car theft related to organized crime on both the victim and perpetrator side. And for the small team of users, they were able to leverage an existing domain graph and add in ad hoc data about the case for the tactical team and drive results significantly faster than the averages across the organization. This group is now fully leveraging Hume and Neo4j against the full set of their cases and have credited several large specific cases and busts in organized crime specifically to these technologies. So there's been a huge impact here, and actually being able to traverse instances of these connected people, as we look at sort of that generic schema I had up front. We have people connected to phones, connected to emails, connected to phone calls. And we're able to connect some specific domain knowledge like telecom information into a more tactical graph where we're also ingesting things like locations and postcodes and areas and crimes, and then traversing all of this information with a team of analysts using essentially click-through behavior. So your analysts are not learning graph, they're not necessarily learning graph theory or learning Cypher or writing query statements. It's all click interactive, and we're able to still leverage that data analysis at scale to get to results faster. It was actually, sort of brief even diversion from my own presentation. It was a really interesting aspect of the sales cycle for this agency, where in the time that we were coming in to sell, they were actually experiencing a specifically relevant case to the community at the time. And we actually leveraged Hume and Neo4j for that case specifically. And it was a missing persons case where time is especially of the essence. And the chief of this investigation essentially ended up saying later that the result we were able to get in 2 days would have taken 2 weeks to achieve in their traditional relational analysis systems. So deploying these solutions at scale can have meaningful impacts to both solving crimes as well as helping to really resolve issues faster and achieve a safe outcome for everyone. Lastly, I want to talk about a counterintelligence use case. This is a representative schema because this is a classified use case where we've built out custom solutions for analyzing massive amounts of geospatial data within Hume and Neo4j, specifically building custom integrations with GeoPandas and Uber H3 to quickly analyze on an ad hoc basis diverse sets of data spanning social media, phone records, dark web data, and beneficial ownership structures across billions of entities. For this use case, co-location of individuals and entities is a key aspect of the analysis. And the screenshot on the right shows a demo we've constructed of the same type of analysis used in a logistics context, but this solution is currently deployed in the counterintelligence space. And again, what we found here is going back to that property graph schema, and even if I go back to this slide, looking at that incredibly highly connected data. In a traditional relational database, you might look at a star schema or a transactional schema, and what you find is that your database often contains one central table eventually, and that table contains sort of as much information as you can cram into it, because actually navigating through the star aspect of your schema is incredibly difficult. Within a graph database, we're able to actually traverse from one side of our data to the other in a performant manner. And so we can bring in much more loosely connected sets of data from dark web, crypto, beneficial ownership, research transactions, papers, keywords, authors, institutions. We can bring all of this data into one schema. And then depending on the analysis that we want to do, using flexible tools like Hume and custom development, we can analyze that data specifically. So in this case, we may be looking at records of millions of people and creating custom ad hoc polygons that we want to explore and seeing what was happening within that polygon. And then you can see on the screenshot here that there are actually paths from, in this case, a logistics use case, the depot to this location. But then might be connections to other people, phone records from calls made while they were in that location. And this is an incredibly powerful way to enable analysts to do what they need to on highly connected data at scale. And I will open it up for questions there. I think I'm ahead of schedule, so see what I
Thank you, Will. Thank you, Will. I just, while we wait for some questions on the chat session, I have a few questions collected already. And if anyone on this phone wants to ask questions also, please feel free to do so. So the first question that's come up is, you talked about the labeled property graph, nodes and edges connected together. And in all the use cases that you showed, there are billions of entities. So what is your storage mechanism for this? Do you go to a data warehouse or a data lake that you use for this? So what's the process for that?
Yeah, absolutely. So there's several storage mechanisms that we look at. So we specifically leverage Neo4j, which is a graph database product in most of our projects. So that's available both as a service or a self-managed instance, typically deployed into the cloud, into GCP, an AWS EC2 instance, whatever it might be. And so in that instance, you're looking at sort of typical storage onto either disk or SSD, as well as caching within memory. What we typically find in large-scale solutions with a number of analysts is that, as I mentioned, we want to also leverage potentially a bimodal store where some of our connected data is being stored in Neo4j, but the other data may be stored in a document store, MongoDB, Dynamo, or a tabular store like Redshift. So even though graphs are a great solution for highly connected data, that doesn't mean that they're a silver bullet for any use case in any type of data. And so what we'll find is actually we often end up with data stored across a variety of store methods. And then we're trying to keep as much of that graph in memory as we can for performance reasons.
Great, thank you. So you mentioned Neo4j and Hume in the same context. Can you describe what's the interface between Hume and Neo4j, and how is Hume leveraging the schema that is used for Neo4j?
Yeah, absolutely. And to just briefly answer that question a bit better, I will share my screen. So right now I have up a Neo4j browser. So this is much like a SQL exploration tool. And so as I open this up, we can see that we have a number of, let me pull up some information here. So this is actually an event-based use case. But so in here, we have some events and we can look at our connected data. And this has some interaction, but it's relatively less customized because Neo4j is just a database. It's sort of equivalent to a Redshift or a Dynamo or a MongoDB, and it's a place for data to be stored. Hume is a layer built on top of that to enable analysis and exploration of that data. So this is another schema that we defined in the Hume platform where we're looking at beer data. So we have a number of reviews about beer, and Hume provides a set of actions and workflows that analysts can use to investigate that data. So I can come up here and I can return a certain beer that I'm interested in. And now we have localized context-aware results that I can look at. So if I click on my beer, I can have a set of actions that my analyst can take. Whereas if I click on my style, we don't have any actions defined. And so as mentioned, we can leverage the power of the graph without having every person exploring it need to understand how this works. And we even have the ability to have inputs and exploration in here where I can actually leverage a parameterized dimensional query exploring out through my graph. So through those reviews, through natural language keywords tagged within those reviews to recommend similar beers to a personal favorite, the Blue Moon Belgian White. And then from here, we actually, again, have more context-aware actions where I can remove other things that aren't interesting from my visualization. And I can ask the question, why are these two things connected? And now I have a separate context-aware action where I can explain that similarity and then run a complex query again to return a nuanced result, looking at the intersection of these two beers. And we can see that we've gone out through those reviews to natural language processed keywords. We can see that the Blue Moon Belgian White and our Brooklyn East India Pale Ale intersect heavily along the flavors of orange and citrus. They're both pretty smooth or light beers, but Blue Moon has a strong coriander taste that the IPA doesn't share, as well as a strong wheat taste that the IPA doesn't share. So not only have we been able to leverage the expertise of my beer expert, but we've also been able to explain why these two things may be related. And if we care significantly about coriander and wheat, these are not a good connection. So we think about applying that to our more specific intelligence use cases, being able to explain the connection between two entities, two people of interest quickly is often really critical. And Hume provides the framework for analysts to interact with the data stored within Neo4j to get to that value.
Great, thank you for that. Very nice, quick demo there. Thank you for that. One last question here. You did talk about the large, highly connected data sets, and then you actually remove data such as documents, right? Mm-hmm. Outside of documents, what do you do to cleanse data?
Yeah, absolutely. So outside of documents, it's, as mentioned in the NLP use case, we might be looking at strings or just long lists of not graphy data. So we often use the word graphy, which is sort of maybe a bit tautological, but the idea being there is data that is highly connected and there is data that is often quite static. You might be looking at slowly changing dimensions. If you were looking at like a company node and you were keeping its head, you might want its location, but if you're keeping like a company overview or just a long string about that, over billions of entities, those nodes, that information stored on the node adds up over time. And so we want to start removing that, because if you look at, typical EC2 instances or other compute instances, and you start getting up around terabytes of memory, it's hard to scale beyond that. It's possible, but it's often easier to start removing some of that data and just keeping our nodes and connected entities within the graph. And the other thing that we can do is actually, we can start leveraging AI to do entity resolution within the graph. So in our research use case, we are loading author instances for every paper and then resolving those separately in a post-processing step into specific entities of authors, because as authors publish papers, they may use slightly different variations of their name, slightly different email addresses or different institutions, and we're using the highly connected nature of the graph to resolve those to specific entities.
Great.
It's another step of cleansing that you might do.
Yep. Thank you, Will. Appreciate it. Lots of good insights there. Thank you for your time and fielding all these questions also.
Yeah, absolutely. Thanks, everyone.
Back to you, Priya.